Section 2.3, this should be a shorter one, assuming I don't get to running my mouth way too much like I normally do. But anyway, let's go ahead and get started. This is about continuity of a function. All right, most of the techniques of calculus require that functions be continuous. A function is continuous if you can draw it in one motion without picking up your pencil, which means that we don't have any holes, we don't have any vertical asymptotes, we don't have anything like that messing with our continuity. So no issues like that. Now we can be continuous over the entire, all real numbers, or we can be continuous over an interval. Either way is okay. The thing is, it's got to be continuous over an interval for us to apply calculus to it over that interval. So that's what we're looking at. Okay, a function is continuous at a point if the limit is the same as the value of the function. And we talked about this a little bit when we were looking at section 2.1, and we said that we had one of those examples where the limit was approaching a value and the function value was the same thing. That's what we're looking at right now. So if the limit and the function value equal the same value, then it's continuous. It's just that easy to figure out. So for instance here, matter of fact, this is the exact graph that we looked at in 2.1. It was not, the limit didn't exist here. The limit did exist here. So we have discontinuities. Here, this is called a jump discontinuity. This is called a point discontinuity. And then at 3, it's actually continuous because our limit from both sides approaches the value of 2, and the function value at 3 is also 2. So it's continuous at 0 and 4 because we can have one-sided continuity as we get closer and closer to an endpoint. So if we go to an endpoint, as long as it's continuous going all the way to that point, we're okay as far as continuity. If these were open, it would not be continuous at the endpoints. Now we have what are called removable discontinuities. The easiest way to think about those are those point discontinuities. If you can put a single point in and make a function continuous, that's called a removable discontinuity. Like here or there, we can fill the hole in. We could redefine this function by putting one extra point into it piecewise and fill that hole and make it a continuous function. Now we also have essential discontinuities which are not able to be fixed. We have a jump discontinuity. We have an infinite discontinuity, also known as an asymptotic discontinuity. And that's where we've got a vertical asymptote, so it's going to go off to infinity, but they never actually touch because they can't cross the vertical asymptote, remember? And then we've got the really weird one that is, it's an oscillating discontinuity. What happens as you get closer and closer and closer to this value right here with your limit is the y value bounces back and forth between a certain value, two certain values, and it goes faster and faster and faster the closer you get to that value that you're trying to take the limit at. We'll look at one of those in class probably. Now, if you want to remove a discontinuity, it has to be a removable one, or a point discontinuity. And for instance, we have f of x equals x cubed minus 1 over x squared minus 1. And it has a discontinuity at x equals 1. We have a common factor, top and bottom, that will cancel out if we were to factor these. And we want to write an extended function that is continuous at x equals 1. So the first thing we're going to do is we're going to cancel out what's cancelable. So we got an x minus 1 factor up here and an x minus 1 factor up here that we can cancel out, there and there. So defining this function, it's going to be x squared plus x plus 1 over x plus 1. Now at that value of 1, it's going to be 3/2. So we've proven that the limit exists. Once we cancel those out, we can just plug this value in, find out what this top equals, find out what the bottom equals, and find out what the limit would be. So for this function, they're both approaching 3/2 from both sides. Now, here's the thing. So we are missing the point at x equals 1, correct? So that means that we have this function right here, x squared plus x plus 1 over x plus 1, but we don't have the point 1, 3/2. We can put that point in with a piecewise function. So here is our original function, or you could express it here and just say x cannot equal 1, same statement, and then 3/2 when x equals 1. We just added a point. So we've got a piecewise function here, and we just added a point in there. Now, the way you can get around that is if you're going to make it continuous, if we cancel these things out here, we can kind of wink, wink, nudge, nudge. We can ignore the fact that when x equals 1, it was undefined to begin with. And we can treat the function x squared plus x plus 1 over x plus 1 as our function, and that's going to be a continuous function when x equals 1. That's another way you can get around it that's a little easier to deal with. That way you don't have to do a piecewise function. Now, I do want you to note, and notice up here, there is another discontinuity at x equals -1, but that's a vertical asymptote. It's not removable. You can't put a single point in there when one goes to positive infinity, one goes to negative infinity, and bridge that gap. It just doesn't happen. And there's what your graph looks like right there. So in all honesty, there is a circle right here that's open, but with this function right here, or canceling the x plus 1 or minus 1's out top and bottom, we plugged in the point. So it made it continuous at that point. Now it's still not continuous here, but it is continuous at x equals positive 1. All right, continuous functions can be added, subtracted, multiplied, divided, and multiplied by a constant, and the new function will still be continuous. Also, if you do composites, remember f of x inside of g of x or g of x inside of f of x, well, if you do a composite of two continuous functions, the end result's going to be continuous as well. So, for example, the sine of x squared. Well, we know sine x is continuous because it goes on forever, domains all real numbers, etc., etc. Hopefully you know that. You can kind of visualize that. X squared is also continuous for all real numbers of x. It's just a parabola. Remember, it doesn't have any holes or asymptotes or anything like that. So when we do the composite here and plug in x squared into sine x, then that is going to be a continuous function as well. And the same thing over there with the absolute value of cosine x. Even with the absolute value and the point, well, we still know that the absolute value is continuous. Cosine, also continuous for all real numbers. Therefore, when we do the composite of that and plug cosine into the absolute value, it's going to be continuous as well. All right, last thing we're going to talk about here for this section is the intermediate value theorem. And it says if a function is continuous between a and b, in other words, over the interval from a to b, then it takes on every value between f of a and f of b. Now, if you think just a second and recognize what all these things are, it makes sense. If we know it's continuous from a to b, what is f of a and f of b? Well, remember, f of x is just y, so f of a is the y value when x equals a. And f of b is the y value when x equals b. So what we end up looking at is this. We've got our y value here, f of a, when x equals a, and we've got our y value here when b equals a, or when x equals b. And what this says is it's going to take on every value between this y value and that y value. So we know, since it's continuous, what's the shortest route between 2 points is a line. So we're guaranteed that we're at the most direct route, we're going to go straight there to there. And what do we know happened? Well, our y value took on every value between this value, let's say it's 1, and this value, let's say it's 5. It would have every value between 1 and 5 in the function. Guaranteed. This is a way that we can prove that some value is in the function itself if we know it's continuous over an interval. That's what we use this for. All right, now, to prove continuity at x equals c, we have to do a few things. First, we have to prove that the limit exists as x approaches c. If the limit does not exist as x approaches c, we can stop. Because if the limit doesn't exist, then the function is not going to approach the same value as we get closer and closer to c. If it doesn't go to each other, let's say they go like this, well then that's a jump discontinuity and we can't fill that hole. Or if it goes off to infinity, we can't fill that hole. It has to go to the same value, so the limit has to exist. And then once the limit has to exist, we have to actually prove it, that the limit exists. We have to prove that the limit as x approaches c from the left and from the right are the same value. If the limit doesn't exist, stop. You can't prove that it's continuous. All right? And then once you've proven that the limit does exist, we have to prove that the function itself has the exact same value as the limit. If we prove that all three parts of this, the left-hand limit as x approaches c, the right-hand limit as x approaches c, and the function value at c are all the same, then we've proven that this thing is continuous. So that's how you would go, and it has to be a statement like this, where you've actually proven all three parts of that. Otherwise, you've not proven continuity. Now, we'll go over some examples of these in class, so don't stress out if this didn't click. When you see an example, I promise it'll be a lot easier to understand.